So, good morning, everyone, ladies and gentlemen, and welcome all of you in this session number 18 of this energy symposium. In this session, we will discuss the impact of oil price fluctuation. I am Franco Del Manzo, and I am Environmental Technical Manager at UNEM. UNEM is the new name of Unione Petrolifera, that is the Italian Oil Industry Association. We deal with the crude oil. So crude oil is the world leading source of energy in this period, and will remain central in all modern economies for many years. Since oil is one of the most important factors in our life, we must pay close attention to the price of this commodity. Today, according to JP Morgan, the world oil demand could return to pre-crisis level at the end of 2021, with the prospect of deficit of oil of 6.8 million barrels per day in 2025. If this happens, price could jump, in opinion of JP Morgan, at very high level. And a shock in crude oil prices would affect the economy in many countries. Therefore, a number of theoretical and empirical research have examined the relationship between oil price shock and economic growth. And in this session, we will see some of these studies. So let me start. Each speaker will have about 15-20 minutes for the presentation, and the audience can send a question in the chat, question as well. The first speaker is Gadebo Oladosu of Oak Ridge National Laboratory, USA. Dr. Oladosu is a senior research economist and has worked at Oak Ridge National Laboratory since 2002. Oladosu conducts economic analysis of energy supply, use, and related policies, along with corresponding environmental implications. Okay, Dr. Oladosu, the floor is yours.
Thank you. Good morning, everyone. It's my pleasure to make this presentation. Can you still see my screen?
Not yet.
So I've got to share it again. Yes, okay. All right. Can you see it now?
Yes, okay.
Okay.
Go.
So on behalf of my co-authors, I will be discussing this topic on US GDP, oil price shocks, and domestic oil production, and ARDL analysis. I will explain ARDL as I go along. The main purpose of this presentation is to address the question, does the change in domestic oil production affect US economic sensitivity to an oil price shock? And the basis for this question is that it has been suggested that domestic oil production can reduce US economic impacts of oil price shocks to zero, but rigorous research is lacking. So the objective of this study is to evaluate US economic sensitivity to an oil price shock, controlling for oil production and trade changes. Ultimately, we're looking at estimating the GDP elasticity with respect to the oil price, which is an important parameter for evaluating measures to respond to oil price shocks. That we need to keep in mind that domestic oil production is one of many potential factors in estimating the economic impacts of an oil price shock. I list here 4 different groups of characteristics that affect estimates that come out of the literature. And these four characteristics interact in complex ways. The first is the characteristics of the oil price shock itself. Size, whether it's supply or demand driven, whether it's temporary or permanent. And then we have domestic market factors, of which domestic oil production is one of those. And then we have the external factors, wealth transfer, terms of trade, and balance of account effects. And finally, we have study-related factors, because we have to model this, we cannot observe it directly. And so it's affected by what model we use, the data, and other factors associated with the study itself. So for the analysis in this study, we collected data from several sources. Most of the oil market data on price, supply, and consumption came from the Energy Information Administration. And the macroeconomic data came mainly from the Federal Reserve St. Louis database on GDP, CPI, interest rates, exchange rate. And we also collected international GDP measures, one for the OECD plus 6 non-members, and Killian's Global Economic Index. All of these variables, except US GDP, are monthly. So it's desirable that we have GDP in monthly terms so we can take advantage of all the other data. So what we did, first of all, was to look into the database of the US economy. And we found that we can actually assemble 70% of the US GDP from monthly components, variables that are in the database. And so we assembled those and then estimated the other 30% from non-quarterly and monthly data. The appendix has an illustration of that process. So this is a visual on some of the data that we used. You can see the almost mirror image between crude oil imports, crude and product imports, and crude production in the US. And then we have the measure for the crude oil price in the middle, which is the refiner crude acquisition cost, a combination of import costs and domestic oil prices to refiners. And the macroeconomic variables, 3 of them are also illustrated here: the consumer price index, and then the calculated monthly nominal GDP, and the real exchange rate. In terms of the method, the ARDL is the autoregressive distributed lag model. It's a single equation method. It's less complex, and it's a starting point for our inquiry. And an advantage of this framework is that we can conduct co-integration tests for a mix of I1 and I0 variables, that is, variables with unit roots or stationary variables. We use the error correction form of the ARDL model in asymmetric form. And the equation is stated here. Basically, they are linear variables that are indicated here by Y and Z, and then asymmetric variables or nonlinear variables. And the asymmetry is basically separating the positive and negative components of that variable and using that in the model. And then we are able to conduct under this methodology the Bands co-integration test, which was presented by Pesaran et al. 2001, and which was extended to the asymmetric form by Shin et al. 2014. And the test is basically based on F and T statistics, which are necessary to validate the long-run parameters in the model. Once we are able to validate the model's long-run parameters, then we can calculate the impact of shocks. The short-run impacts are the coefficients on the first difference variables, and the long-run coefficients are a combination of the long-run on the lagged variables themselves for the dependent and independent variables as stated here. For the implementation of the model, again, the dependent variable is the monthly real GDP. All variables are in natural logs except the federal funds rate, which is already in percentages. And monetary variables are in real 2015 dollars. The independent variables in the model are listed in the table to the right, with only the oil price, which is our focus, as the only variable with asymmetry, that is separating the positive and negative components. We performed initial variable tests, unit root and structural breaks, using the ADF, the augmented Dickey-Fuller test, the KPSS, and the Zivot-Andrews test to test stationarity and the presence of structural breaks in the variables. And then we performed model diagnostics, testing for weak exogeneity of the regressors, which is one of the requirements of using the ARDL and bands co-integration method, as well as autocorrelation of residuals, normality of residuals, and then perform the co-integration tests. So the unit test results show that most of the variables, at least under the ADF and the KPSS, have unit roots. Their first differences are stationary. But when we use the Zivot-Andrews test, which accounts for potential structural breaks, it suggests that structural breaks may be important. And this we see in that petroleum import and consumption are found to be stationary once we account for structural breaks. And we find mixed results for the two other petroleum quantity variables as well. So in essence, we have a mix of I1 and I0 variables here when we consider structural breaks. And so we can implement the ARDL model as long as none of the variables are greater than I1. So in addition to the variables that I discussed earlier on, we included monthly dummies excluding January. And because of the structural break findings in the tests, we included structural variables based on Enders et al. 2016. And one outcome of that was that the number of lags needed in the model reduced to 4 instead of 8 initial lags. Based on the initial model, we looked at adding dummy variables to represent the Great Recession period and other dates that appeared as outliers. And the final model, the diagnostic for the final model are illustrated in the chart to the right. The model passes the stability test and mostly passes the other tests of normality, heteroscedasticity, and the plot of Cook's distance versus leverage, with a few outliers being responsible for some non-normality and heteroscedasticity. So what we did was to use an heteroscedastic consistent covariance estimator to account for remaining issues in the residuals. Once we finish the diagnostics of the model, we'll then perform the weak exogeneity test and found the regressors to be weakly exogenous, which means the ARDL model will be valid in this case. And then we performed the Barnes co-integration tests. The asymptotic F and T tests were inconclusive, but McNaughton et al. 2018 proposed a bootstrapped approach to deal with that. And so we implemented that. And the result was that the real GDP is co-integrated with regressors. And so we're able to validate the long-run parameters of the model and can use the model to estimate impacts or use the coefficients. So we move on to interpreting the coefficients themselves. And we find for the positive and negative oil price component that there are significant US GDP impacts. The impacts are negative for the negative oil price component is significant in the short run, but for the positive oil price component, it's significant in the long run. For the real GDP coefficients themselves, the long run coefficient implies that the GDP adjusts back to equilibrium at the rate of about 17% per month, which means after a shock, the economy will return to equilibrium in about 4 to 6 months. And the short-run coefficients are also negative, suggesting that a positive change in the US GDP is followed by a negative change, which is necessary to bring it back into balance. And the other aspect of this study was to see if one, oil production and import coefficients will be significant determinants of the GDP, and whether adjusting for them in the model would reduce the significance of the oil price. But what we found is that both oil production and import coefficients are all insignificant, whereas the petroleum consumption coefficients are significant in the long and the short run. The long run is positive and the short run coefficients are negative. And so given that the variables are in logarithms, the short run coefficients are actually like short run elasticities. And the equation for calculating the long run impacts that I showed before can be used to calculate long run elasticities. So we did that for coefficients that are significant in the long run. And for the oil price, the positive oil price, which has a significant long run coefficient, the estimated long run elasticity is minus 0.022. For the other significant long run coefficients, the magnitudes of the elasticities appear large, but they're not implausible in all cases. For example, the OECD +6 GDP index has a value of 0.62, and given the role of the US in the OECD and the fact that the global economy tends to move together, 0.62 is not too large. But in other cases, for example, the CPI, the positive long run elasticity is unexpected. Our interpretation is that even though the single equation model is valid, there may be interactions among the independent variables themselves that we're not able to capture within a single equation framework. And so in summary, and also to lay out some future work, we find that the estimate of US GDP elasticity with respect to the oil price from this study is consistent with previous meta-analysis findings. And the recent literature also provides some supporting evidence. Those literature are not adjusting for domestic oil production, but they are showing that the GDP elasticity or the sensitivity of the US economy to the oil price shock is stable over time. So that supports the general conclusion that we find that the estimates are similar to past estimates. The second bullet is then talking about the domestic oil's role in GDP impacts of oil price shocks, that may not be in changing that it may be in changing the nature of the oil price shock itself. That is, it might affect the size of the shock or its persistence, but not the marginal GDP response to a given shock size. So increased oil production and changes in global markets following that might reduce the potential to observe an X amount, but if we do observe an X amount of the shock, the effect on the GDP is stable over time. And the GDP elasticity is measuring that marginal GDP response, not the size of the shock itself. So for future work, we will explore the simultaneous equation framework to account for some of these other issues that I mentioned, to capture explicit interactions among variables and potentially changes in the oil price shock itself. Thank you.
Very well, very well. Thank you very much, Mr. Oladosu, for your very interesting contribution. Now we have the presentation of Neil Wilmot of University of Minnesota. Dr. Wilmot is an associate professor of economics at University of Minnesota, with particular interest in energy economics, applied econometrics, social capital, stochastic processes. Dr. Wilmot, the floor is yours.
Thank you for that. Thank you for having me. I will share my screen. Hopefully now you're seeing that.
Yes.
Okay, great.
Yes, perfectly.
Thank you. All right, so you mentioned a number of my interests there, and what I like about this work that is ongoing and still very early in its stages of progress is the idea that it brings together a number of those interests that I've sort of been working on over the last 10 plus years now. So I am going to talk to you about the idea of looking at sort of the co-movement or the idea of a global pool hypothesis in oil markets, right? And so this idea that the world oil market is like one ocean, one great pool, dates back to the work of Morris Adelman back in 1984, right? And if this were true, then prices would track one another very succinctly, very closely, right? Sorry, I got an issue here. Okay, there you go. So they would move very close together, which is often what we see, but not always what we see, right? And particularly more recently, we've observed pretty large price differentials between different streams or blends of crude oil, right? So if you look, for instance, at two benchmark crude oil price series, right, over the last 30 years, right, you can see that there is, they track very close together through the first 2/3 of this, but there are some times in which there is a difference, significant difference between them, right? And more recently, right, that relationship is sort of inverted, where now Brent trades at a higher price than does West Texas Intermediate, right? And so if we look particularly at this period of difference, right, zooming in to that period, right, you can see there are, there's a gap, but the size of that gap varies depending upon, right, the time period you're examining, right? And unique to this figure, which admittedly I want to thank the AIEA for producing for me, which I listed from them. But you can notice, right, one of the more important and regional blends in North America has become the one that's coming out of North Dakota, the Bakken oil, and you can see that it tracks very closely to WTI, though again it also, right, has some significant deviations, right? And so the question really is, right, what can I say about this global pool hypothesis? And you know, this theory has been tested a number of different ways, right? And so how can I investigate this using a new approach, right? And so that's what I'm attempting to do in this research. So this idea of a differentiation has been recently noted by Dar in 2019, right? Who specifies that in the post 2010 era, it seems as though there has been a growing divergence between these benchmarks, right? And suggests that this provides evidence that the two markets have been regionalized. Right? And so regionalized for WTI would really mean, right, North American crude oil market. So what I've done is I'm investigating the relationship among this complex of North American crude oil blends, right? And I'll talk more about which ones are involved in that shortly. But I really want to sort of identify or point out that really what's happening here is I'm bringing together sort of three distinct lines of research to sort of, you know, to answer this question. One is obviously the global pool hypothesis, which I've already talked about, right? But as I mentioned, a number of authors have investigated, right? Hamuday et al. In 2008, right, used a threshold co-integration technique to investigate whether or not there was a global pool, right, and used an asymmetric error correction model, right, to get at the speed of adjustment towards that equilibrium, right. In some of my own work, right, I've used co-integration techniques with structural breaks, right, to investigate the relationship among regional blends along with a benchmark crude oil, right, and found a significant co-integrating relationship, right. So a number of others have used either co-integration or causality to investigate this idea, right. I want to take a slightly different approach. And so the approach that I'm looking to get at here involves these last 2 points, right? A lot of my research and a lot of other recent research has investigated the stochastic process that underlies the crude oil price, right? So it's often assumed that there is some sort of, you know, geometric Brownian motion type process that defines how prices evolve. Right. And so more recently, the addition to this this assumption has been that we need to incorporate an element that's going to allow for jumps. In fact, at the beginning of this presentation, right, there was talk of how prices have jumped recently, and they jump around, right? And so that really is what's referred to as a discontinuous stochastic process, and a number of individuals, including myself and my co-author, Professor Mason, right, have investigated this idea. So Ascari and Krishin, right, Lee et al., and others have investigated and found a significant jump component, right? That is the process is improved by including or allowing for this continuous move. Having said that, you know, Postali and Pichetti, right, early on investigated this and compared it to a simple geometric Brownian motion process without jumps, right, and said that, yeah, jumps improve things, but come at a cost of complexity, right? And so maybe geometric Brownian motion might be all right. So I'm gonna allow for jumps, right? And I'm gonna incorporate that into sort of the next point, which has to do with sort of the time varying volatility feature of oil prices, right? There are times in which oil prices are relatively calm. There are times in which oil prices are relatively not calm or unstable, right? And we see this idea of time varying volatility, which dates back to the work of Boleslav, right, and others. Pindyke has investigated a Garch process in natural gas markets. But most of those are univariate in nature, and more recently, what's been applied is a multivariate Garch type model. So we have a system of equations, and what that does is it allows us to capture spillover effects between markets. So does the volatility in one series, right, spill over and influence the volatility of another series? And Efimova and Solidis in 2014 investigated, many of these energy commodity markets, natural gas, crude oil, right, and found a spillover effect, right? And so I want to combine those, I think, in a unique way, in a novel approach, right, and hope to say something about the combined nature of these markets, right? Is there one pool? How related can they be? Can we quantify this relationship among these regional crude oil blends, right? So here's the methodology then. It's based on this model introduced by Chan and Maheu in 2002, right? And it's known as the autoregressive jump intensity model. So the idea is that the returns, right, follow a process that allows for jumps. Those jumps, right, are normally distributed with some mean and some variance, right? So we have normal distribution, right? Some mean jump size could be positive, could be negative, right, with some variance, right? What's key for us is that the number of jumps arriving between any point in time is described by some discrete counting process, and we're going to model this process as a Poisson random variable, right? And so really what we're interested in is this jump intensity term, which we're going to call lambda t, right, and describes, right, how many jumps occur in any particular element of time. So what's the jump intensity? And it turns out when you estimate this model, right, then you can determine, you can back out of that model a series of lambda t values, right? And to do that, you have to formulate a model for how lambda t evolves. And so, following what Chan and Maheu did, right, they modeled it as an autoregressive one process, right? Then I'm going to follow the same methodology, and I'm going to obtain this series, right? It's time dependent, right, of jump intensities. Right? And then based upon this time series of jump intensities for all the different crude oil series that I have, right, I'm going to look at and use sort of these volatility models to investigate whether or not there's any spillover in this jump intensity. Right? So if there's a high jump intensity in let's say WTI, right, then is there also does that spill over into one of the other regional Louisiana light type series, right? And so to do that, I'm going to have to first establish that this term is actually time has some time varying volatility in it. So I'm going to use some univariate Garch 1-1 type modeling to establish that. And then once that's established, then I can rely on terms of the multivariate Garch type modeling to try and infer what that relationship is. And so there are a number of different methodologies that could be used in the multivariate Garch modeling. Admittedly, since this is early in the research, I'm sticking with the least complex type framework, the conditional correlations, right? As you increase the complexity, right, you scale up the number of parameters that are estimated, you ask a lot more of the data. So I want to establish that first this works before I get into, you know, trying to really test the model, break the model, right? So really what we're interested in then is the correlation coefficient, right, which comes out of this gamma matrix, right, that defines the time varying volatility of the model. So let me speak a little bit about the data, right? We have the benchmark series of WTI, right? And we have then 4 other North American regional blends. We have Louisiana Light Sweet, we have Mars, Louisiana Heavy, and Mexican Maya, right? And these, if I go to the bottom here of the table, you can see that these represent, right, various combinations of light sweet, light sour, heavy sweet, and heavy sour to give us a range of characteristics, quality characteristics for the data, right? So we can see across that spectrum of characteristics how this relationship works, right? I've got, you know, the summary statistics across the log changes in prices. I'm dealing with returns, right? You can see there is some skewness and some excess kurtosis, right? So we have some fat tails, which is also common feature of you know, oil prices and markets in which we see jumps occurring. This just again gets at the quality characteristics. You can see that I've again borrowed it from the EIA, but you can see there is, right, some differences amongst these blends. So that helps to say that this relationship goes beyond just the simple same quality, same characteristic type crude oil series. Working with time series data, right? So to need to establish the stationarity properties of the data, right? Not surprisingly, I'm working with returns, right? And so these tend to be integrated degree 1, right? So they're non-stationary in level, but stationary in differences, which is what I'll be working with. So that's property is satisfied. Right? Okay, so step 1 is to estimate that the ARJI, the autoregressive jump intensity model, right? And so I've done that for each of the series, right? You can see there's a number of coefficients, right? And nobody likes a table that has a lot of small print on it. So let me just highlight for you what the key takeaway from this table is, right? Is highlighted by this line. What we're interested in is lambda, right? And so I've estimated for both a constant lambda and then lambda, the autoregressive process, right? And you can see that lambda is statistically significant across all the series, right? And so that's the key takeaway, that jump term. Jumps are important for these series, right? And we can model it with this time varying element, right? And it is statistically significant, right? And so then based upon that in the autoregressive process, right, we obtain a time series for lambda, which we call lambda hat, right? This time series of intensities. And then I need to establish that this is this follows a Garch process, right? So I've done univariate Garch modeling for each of the series based upon lambda, taking that lambda t, running it, you know, on a simple Garch 1-1 type framework, right? And again, the takeaway here is that yes, there is some time varying volatility, you know, the alpha 1 and beta 1, right? The squared innovations and the lagged volatility is statistically significant for all of the series, though I note that for one, it appears that an arch model might make more sense, right? But for in general, right, I take it as okay, there is some time varying volatility, which would then allow me to use this multivariate Garch type modeling, right? And so again, we've got a bivariate Garch model, right? So I'm just running in this framework. I'm examining the relationship between the benchmark WTI and each of the regional blends, right? So you can see that given across the top, right? I've done it for WTI and Louisiana Light, right? And what's key to focus in on this particular slide is that constant correlation coefficient, right? Is it statistically significant, right? And in each case, right, it is statistically significant and quite high, right? And so there does appear to be this consistent correlation amongst these jump intensity terms for each of these bivariate models, right? So when there's a high degree of jumps in WTI, there's a high degree of jumps in Louisiana Light or in Maya, right? Maya tends to be the lowest one at 0.75 as the correlation coefficient, right? But still rather high degree of correlation amongst the jump intensity terms, right? And you know, for the rest of the terms, they are all statistically significant, which gives me hope that what I'm doing makes sense, right? And again, as I mentioned, right, I'm only doing it for this constant correlation multivariate Garch model so far. I intend, right, to do it for others, but so far, what I'm
Dr.
finding
Wilmot,
is that
2 minutes to conclude.
Yeah, this is 2 slides left. Well, this is what summarizes what I've done, and the next one's what I'm going to do. So the jumps fit well, statistically relevant, right? That time varying volatility is important, statistically valid, right? And based on this multivariate Garch estimates, there appears to be a significant degree of correlation amongst those contemporaneous shocks, or those jump intensities, right? So then next would be to move beyond the CCC Garch into something that allows for a more complex relationship between the series. So the BEKK specification, or the dynamic conditional correlation model, right, seems to be relevant. 2 issues that I think I'm going to have to deal with: structural breaks, which we heard from for the first speaker, right, is important, right? The shale oil revolution in the U.S. is probably something that is likely impacting this, right? And so maybe given the time frame I'm looking at, maybe a before and after seems important. And then I really am interested in going beyond those that I have. The Bakken price series is where I want to investigate, along with Canadian prices and also other regional prices from around the globe. But that's where I'm at. That's where I'm headed. That's all I've got. As my time's up anyway, so I think that works out well. Thank you.
Thank you very much, Dr. Wilmot, for also to you for your very stimulating research. And now we have the last speaker, Dr. Rocio Uria Martinez, also from Oak Ridge National Laboratories. Dr. Uria Martinez is a research and development staff member in the Environmental Risk and Energy Analysis Group. A research address modeling energy system and markets accounting for the interaction among physical, engineering, economic, and regulatory aspects. Dr. Uria Martinez, the floor is yours for your last presentation of this session.
Thank you, Mr. Del Manso. Let me open the slides. Good morning, afternoon, or evening, depending on where everybody is. It's very early morning here in Tennessee. The work I'm presenting today, titled An Exploration of the Role of Petrochemical Demand on World Oil Demand Elasticity, is in collaboration with my other ORNL colleagues listed on the slide. And the 2 questions we are trying to answer is, first, how elastic is oil demand in the petrochemical sector? And just to take this out of the way, when I talk about oil in this presentation, it includes also natural gas liquids. And the second question is, will world oil demand elasticity increase or decrease as the petrochemical sector share of oil demand increases? The motivation to look at these questions is, on one side, the fact that the petrochemical sector share of oil demand is expected to increase in the coming decades, and that the oil demand elasticity literature has paid very little attention to the petrochemical sector until now. My plan for this presentation is to briefly describe oil use trends by the petrochemical sector in the US, quickly refer to some related and relevant literature, and then present the results from empirical estimation of US petrochemical oil demand elasticity, and conclude with a qualitative comparison of those estimated elasticities with the elasticities for other demand sectors. Chemical feedstock is projected to account for 30 to 50% of global oil demand growth out to 2050. This is the consensus view in business as usual projections by the main oil market forecasting sources. For example, IEA, as a result of that strong growth, predicts that the chemical feedstocks share of world oil demand grows from 12% in 2017 to 16% in 2050. Still not a huge amount, but at that point it would be the largest non-transportation use of oil. And this strong growth is underpinned in particular by the expected large increases in demand for plastics in non-OECD countries. There are, however, some uncertainties around this business as usual projection that have to do with policies that are starting to be enacted to address environmental concerns about the use of plastics, and also ongoing R&D to look for alternative feedstocks for the production of chemicals, for example, biomass. But we don't know by how much or how fast these aspects could offset the expected business as usual growth. Now, if we are gonna study the oil demand in the petrochemical sector, we have to focus on the steam cracking process, which can take a variety of inputs as feedstock, which in this diagram will be naphtha, gasoil, ethane, and propane are the four we are going to be looking at in this analysis, and convert them into a mixture of products, ethylene, propylene, butadiene, and aromatics, that then are converted once again into plastics, resins, fibers that go into consumer products of all kinds. And in the diagram, I also show the steps involved in converting what is extracted from the ground, either crude oil or natural gas, into the feedstocks going to the steam cracker. For naphtha and gasoil, it is crude oil going to the petroleum refinery and separated into a bunch of different streams. Two of them, naphtha and gasoil, go to the petrochemical sector, to the steam crackers. And for natural gas liquids are separated out in a fractionation plant, and two of those, ethane and propane, are also used in steam crackers. Now this plot shows that most US steam crackers use multiple feedstocks. This is data from the Oil and Gas Journal and refers to the year 2015. It shows for every steam cracker facility that was operational in the US in 2015, what was the typical feedstock mix. Since then, there has been quite a few new steam crackers coming online, and most of them would be green bars here, ethane-based mostly. Looking at this plot, we see that most steam crackers use at least two, three, even four feedstocks. And so we might conclude from it that there is quite a bit of flexibility to adjust the feedstock mix. However, we cannot be sure of that right away because this picture can be achieved in different ways. Each of these bars corresponds to a steam cracker facility, but then within each facility, there are multiple furnaces, multiple units. And so it could be that the various units use different feedstocks, but each of them is kind of dedicated to one type of feedstock. Or it can be that they have truly flexible furnaces that can relatively quickly switch among feedstocks. We don't have the detailed technical specification of what each steam cracker can do. And so with the empirical estimation, we try to tease out a little bit how much flexibility we observed in the feedstock mix that the steam crackers are using. And then this is the second part of the motivation. As I mentioned at the beginning, the petrochemical sector has received very little attention in the oil demand elasticity literature until now. One exception is this 2010 paper that estimated elasticities for the petrochemical sector, short-run elasticities between -0.015 and -0.04 for OECD and a group of income-growing countries, and not statistically significant elasticities for China and oil-exporting countries. What is more common is to have elasticity estimates for the aggregate industrial sector. But I would argue that those don't necessarily apply well, are not applicable to the petrochemical sector. Because in most other industrial sectors, oil is mostly used as process energy. So to power heating, cooling, and different machinery you need to carry out the industrial processes. But in the petrochemical sector, 60% of the energy is used as feedstock energy. It's it itself converted into something else. So the aggregate industrial demand elasticities are going to refer mostly to process energy, while in the petrochemical sector, most of the energy is consumed as feedstock energy, and the attention that is paid to prices in one versus the other might be different. It's also worth noting that in the broader energy economics literature, there is recently more interest in petrochemical markets. I'm listing here a bunch of studies that focus on the petrochemical sector, but they tend to focus on price dynamics. So what are the price relationships, the degree of price transmission, when there is a shock, for example, in crude oil or natural gas, how that transmits down the supply chain, and whether there is also price transmission in the other direction. So that is being done, but no estimation of elasticities. These plots show key supply and demand variables related to the 4 feedstocks we are looking at in this analysis. So if we look, for example, at the ethane panel, the yellow is the net production, the blue are net imports, the green ending stocks, and the orange is product supplied, which this is the definition for product supplied, is a proxy for domestic consumption, and will be the series that shows up in the left-hand side of our demand equations for estimation. But I think it's good to look at these descriptive plots of each of the feedstocks, because there's important differences across the markets for these feedstocks, or the supply-demand balance, let us say. Both the quantities being used, and these are quantities that go to the petrochemical sector, in the product supply variable, are very different, much larger for ethane and propane than that for the refinery source feedstocks, naphtha and gas oil. Also, the US is a net exporter for ethane and propane, but a net importer for naphtha and gas oil. And the stock-to-use ratios, where for the use part of that ratio, I include both product supplied and exports, are much higher for ethane and propane than naphtha and gas oil, kind of saying that there is more of a buffer, for example, in case that there is a supply side disruption for ethane and propane than for the refinery source feedstocks. And now kind of moving to the empirical estimation portion of the talk, the question we are trying to answer specifically is how much does the mix of refinery sourced versus NGL-based feedstocks respond to changes in the crude oil and natural gas prices. And I've been talking about 4 feedstock series, but for the empirical estimation, we combine them into 2 groupings. So the oil feedstock series includes naphtha and gas oil. Those are the feedstocks that come from the petroleum refinery. And the NGL feedstock series includes ethane and propane. The two price series we are using are for oil, WTI, and for natural gas, the Henry Hub price. And we also include industrial production index as another independent variable. The data we are using is monthly from January 2010 to February 2020. And we adjusted, we took the seasonal component out of all the series for estimation. And also they are all in logs, all the variables, so that the estimated coefficients can be interpreted as elasticities right away. And as you've heard on the previous two talks, time series analysis, first step has to be unit root tests to determine the stationarity. We conducted 3 different unit root tests. 2 of them, the ADF and Phillips-Perron test, have as null hypothesis that the series contains a unit root, and the KPSS one that the series is stationary. In this table, I show the results from the 3 tests for each of the series shown in the previous slide. And by looking at the conclusions from the 3 tests, we get to a conclusion in this code. For the price series and the industrial production series, all the tests agree. Those series are non-stationary, there's a unit root. But for the quantity series, the oil feedstock and NGL feedstock consumption in the petrochemical sector, the conclusions from the different tests are conflicting. So we cannot make a determination from this test of whether it is an I1 or I0 series. And for that reason, in order to be able to test for the existence of co-integration between the variables in each of the demand equations, we use the Pesar and bounce test. So these steps are, a lot of them, Devo already went over them in the first talk, so I will not spend much time on this. But for the Pesar and bounce test, the first step is estimating an autoregressive distributed lag model. And in this case, for a demand equation, that is an equation where we have the consumption variable in the left-hand side, and on the right-hand side, lags of the dependent variable, and the contemporaneous and some lag variables of the own price, the price of the substitute feedstocks, and the industrial production index. The first step is selecting the optimal lag order of the ARDL process, and in the table I show what we picked for each of the equations based on the base information criterion. And then the next step is to conduct a bunch of different tests on the residuals of the selected ARDL models. Both equations, the one for naphtha plus gasoil and the one for ethane plus propane, passed the 4 tests for serial correlation, normality, structural change, and heteroscedasticity. And these are visual representations to go over the different tests, but I will not stop on them in the interest of time. And since the tests, the residuals pass the tests, then we can conduct the actual Pesar and bounce test, where the null hypothesis is no co-integration. And based on the p-values from both the F test statistic and the T test statistics for the Pesar and bounce test, we can reject the null hypothesis of no co-integration. Therefore, we can extract both short-run and long-run elasticities from the ARDL equations. And these are the results from estimation of the ARDL equations. In this slide, I show the results for the refinery source feedstocks, naphtha plus gasoil. And I'm going to focus just on the coefficients on the price variables. So for naphtha plus gasoil, the own price elasticities are the estimated coefficients on the WTI variable. If we combine the estimated coefficients on the contemporaneous variable and the 2 lags, altogether the short run response is pretty small, but would be overall slightly positive, which is not what we would expect for an own price elasticity. However, the responsiveness to price peaks for the first lag component, and for that first lag, it is a negative estimated coefficient. One possible question to ask here is whether, how much information the contemporaneous value of the WTI price has. So for the naphtha and gas oil that are being consumed in a steam cracker in December 2020, how much of it was purchased at December 2020 spot prices? It might just be that is not the, that the contemporaneous price doesn't have too much information for the consumption in this month. And for the cross price elasticity is something similar. The response peaks for the first lag coefficient, and for that coefficient, it has the expected positive sign for the cross price elasticity relative to a substitute. But the contemporaneous, the estimated coefficient of the contemporaneous value has the opposing sign. And then the long run elasticities, the own price one is not statistically significant, and the one with respect to the Henry Hub is positive and statistically significant. For the NGL-based feedstock equation, ethane plus propane, none of the short-run price elasticities are statistically significant. They all have pretty large p-values. But the long-run elasticities are both statistically significant and have the expected sign. So the elasticity with respect to the own price, which in this case is Henry Hub, is negative, and the one relative to the oil price is positive. Now I'm going to skip over this one, and going back to the second question we had in the first slide. So given these estimated petrochemical sector elasticities, should we expect that the world oil demand elasticity increases or decreases as the petrochemical sector share of oil demand increases? If we think of global demand oil elasticity, building it as the weighted average of elasticities in the different demand sectors, and I show here for comparison global sectoral elasticities that we obtained from a meta-analysis conducted in 2018, and we compare them with the net petrochemical sector elasticity for the US that we just estimated. The conclusion would be that as petrochemical sector share increases, oil demand elasticity decreases, because what we are getting is, in the short run, but combining the elasticities relative to the WTI price for both the refinery sourced and NGL-based feedstocks, we get a very small, but almost zero basically in the short run elasticity, and 0.12 still small but positive, so the opposite sign to the elasticities in other sectors. To conclude, I would go back to the initial statement that the share of the petrochemical sector in world oil demand is expected to increase in the coming decades. And I think for that reason, trying to understand the ability of steam crackers to adjust their feedstock mix to shocks when there is a shock in the oil or natural gas price is important to understand as a lever and from an energy security standpoint. The estimated price responsiveness for the US petrochemical sector using data for the last decade is that in the short run is very small. So we don't find evidence here of a lot of short run flexibility in switching between refinery source feedstocks and NGL feedstocks. But to assess the effect on global oil demand elasticity, I think we should not just limit ourselves to understanding US petrochemical sector elasticities, but we also need to look at those elasticities in other regions of the world, particularly because in the US, natural gas liquids are the dominant feedstock, but in most other regions of the world, it is naphtha-based steam crackers that account for most of the petrochemical sector activity. And those tend to be highly integrated with petroleum refineries. So the response that the steam cracker can have to changes in oil and natural gas prices also depends on what's happening in the refinery. And I think all those relationships, understanding those, deserve some further analysis and attention. And with that, I conclude. Thank you.
Okay, thank you very much, Dr. Uria Martinez. For now, we haven't received any question, and so I think that we can conclude the session. I would like to thank you very much, all the panelists and the participants. Panelists for the very interesting, important issue they have presented in this. So if we receive some question, we will share with you, and we can stop the session now, saying goodbye to the panelists and to the participants. So have you a good day. Bye bye.
Thank you.
Thank you.
Bye bye.
Bye.
Thank you so much and have a good day. Goodbye.
Bye.